Okay, so do we have any lingering homework questions? Yeah,
What's the homework then? Is that what it's-
that's what I figured.
Yeah.
Um, okay. Okay.
I think it's number 5 on that one.
Number 5. Okay, so you're given a line and intersecting the YZ plane. Okay,
Why is it 0?
whatever variables you have in the description of a plane, you take the other variable, one that's left out, x. You would set the x coordinate equal to 0. Yeah. Oh, is that not what you did earlier? Or
No, yeah, I didn't see. But
okay, so yeah, so you set y equals 0.
it seems simple. All I did was solve for y and then plug it into the parametric equations.
Okay, yeah.
Put it into the points.
Yeah, now, this is, since it's asking for a point, so you use parentheses, and it didn't take it? Oh, okay. Oh. You had the t in the wrong place, you had t multiplying this, it's supposed to, t is multiplying the,
Oh.
okay. Right. Okay, other ones?
You do 4.
4.
It's easy. It's the same.
It's this same approach. Oh, wait, this is a different problem. Okay, so finding where lines intersect. Okay, so since the lines use the parameters t and u, so you would set the x components equal to each other, y equal to each other, z equal to each other. So you're gonna have 3 linear equations in the 2 unknowns t and u. So that's the approach I spent a ton of time on in class, where you pick 2 of the equations and
Okay.
solve it and then see if the third one is satisfied. Okay. Anything more? Well, okay then. I don't have a whole lot for today either.
Short class.
Yes, that's the plan. Okay.
Like, hold on, this is pretty great.
I apologize if that means a long class later, but I don't think it's gonna happen. Okay, so we're getting to the final portion of the course. Parametric curves, and later polar coordinates. This week is about parametric curves. And some of this knowledge will come in handy in Cal 4. I know. So, now, so there's various ways to describe curves in the XY plane. Actually, everything I do, yeah, everything I do at least today is gonna be just in 2 dimensions. All right. So what's most familiar to you all is y being a function of x. And so that's convenient for many reasons, but you can think of curves that cannot be described using an equation of that form. So this is only helpful if the curve passes what's referred to as the vertical line test, which is necessary for y to be able to be described as a function of x. And by vertical line test, I mean, if you draw a vertical line through a curve, it can only cross it at one point, at most one point. So what would be an example of a curve that cannot be described by having y as a function of x? A circle. So you can only do, so you can do a semicircle, but not a circle. So it's limited in what you can describe. And then if I call this 1b, x equals f of y, you can try that. But that has the same similar limitation. If so the curve must pass a horizontal line test in that case. So if I have a curve like this, it's a parabola, but it's facing the wrong way or different way than what you're accustomed to. So I could not describe this using y as a function of x, but I can use x as a function of y. I could have x equal to y squared, for instance. And so we don't need x equals f of y very often, but once in a while it's useful. The second way, that is the focus of today, does not have this kind of restriction. Parametric equations. That have a form x is some function of a parameter t, and y is some other function of the same parameter t. So t is referred to as a parameter, and t has some domain AB. So a curve does not have to pass a horizontal or vertical line test to be described using parametric equations. Any curve can be described parametrically. Simplest example, one that could not be done before, circle. That has radius of r and a center. We'll make a center at an arbitrary point, x naught, y naught. So the x coordinate would be your center x naught plus r cosine of t. And then y would be the y coordinate of center plus r sine t. Now, if I were to then look at x minus x naught squared plus y minus y naught squared. Well, x minus x naught is r cosine t, that would be squared. And then y minus y naught, that's r sine t, and that would be squared. But then what happens, what do I get if I simplify this? No, close, but
Oh, it's just I squared.
yeah, r squared. Which is what you'd expect for a circle of this center and this radius. That using standard form of the equation of a circle, x minus x on squared plus y minus y naught squared should be r squared, and sure enough it is. Okay. Yeah, because you're only getting part of r squared from here, and part of it from here. Yeah. Okay. Now, if you started with this equation that relates to x and y, yeah, you could try solving it for x or solving it for y, but at some point you'd be taking a square root. And you find that you can only describe half of a circle with y as a function of x or x as a function of y. And if you choose like the positive square root, then you have to choose the negative square root to describe the other half. Whereas parametric equations, you don't think about that. You just have an equation for x and an independent equation for y. Right. Now, you can also have more than one set of parametric equations to describe a given curve. So here I have like a typical way of describing a circle. So if I specialize that to the unit circle, where the center is at the origin and the radius is 1. So I can call these the default parametric equations. For the unit circle, that says x is equal to cosine t, y is equal to sine t. But I could give other parametric equations. Let's see if that would also describe the unit circle. I could let x be equal to sine of e to the t, and y is equal to cosine e to the t. Okay, and also here the default domain e would going from 0 to 2 pi. We trace out the entire unit circle. Whereas here I could specify the domain for t to start at the natural log of pi and end at natural log of 3 pi. So if I were to simply use either one of these six parametric equations to plot the curve, I'd have the same result. What I'd be looking at is a unit circle. But how that unit circle is traced out is different for these two sets of equations. So if I'm going to use these parametric equations to plot the unit circle, there's a couple things to think about. One is a few things to think about. One is, where do you start? What's the starting point? Also, what is the direction or orientation in which the curve is being traced out? And what about the speed? So this one, if I use my starting parameter value, t starts at 0, where's my unit circle going to start? Like, where would I put my starting point here in my xy plane? well, what is equal to 0? T is 0. Well, so what xy point would that give me? Yes, x is 1 and y is 0. So that's the starting point. Okay. So now, as I let t increase from 0 to 2 pi, I'm going to get points on the circle. Now, if I'm going to trace out a circle, I could go clockwise, or I could go counterclockwise. Which one's going to happen in this case? It's going to be counterclockwise. It's going to start here and go around like that, and then end where you started. Okay. Now t corresponds to radians, so it's going to trace up the circle at a uniform pace. Like if I were doing an animation of this, plugging in t value, evenly spaced t values, so there's like a one-to-one correspondence between like t being time and also radius, like distance along a circle. It would trace it out at a uniform rate. And I point that out because let's see what happens with the other parametric equations here. Okay, so for this one, where t is starting out at the natural log of pi, but then whatever t value we get, we're going to exponentiate it and then take sine and cosine. So where's this circle going to start? Yes. Yeah, so when t is equal to natural log of pi, you plug in natural log of pi here, but e will cancel the log, so you have sine and cosine of pi. So the x coordinate will be 0. The y coordinate is cosine of pi, which is -1. So that's your starting point. Okay. So then I'm gonna go either in this direction or in this direction to trace out the circle. Which direction is going to be? Is it going to go? Okay. Okay. Yeah. How's it going to go? But so, what happens is I have since t is starting at this point, then when I by increasing t values, I'm going to have something that's somewhat greater than log pi. So I'm going to have something somewhat greater than pi to take a sine and cosine of. So if I plug in something that's a little greater than pi, it's a sine. Is that going to give me something that's positive or negative? Negative, yeah. The sine starts out positive going from 0 to pi. Once you get past pi, sine goes into the negative values. So it's actually going to trace out the curve starting in this direction. It's going to go clockwise. So the opposite orientation. Once you get to 3 pi, you'll be back where you started. Okay. Okay. What about the rate at which the circle is being traced out? Because we're taking instead of sine or cosine of t, like in the original equations, now it's sine or cosine of e to the t. So you have to think about how the exponential behaves. like if I look at the function e to the x.
What was the question?
Okay. Like. Basically. An indication of at what rate the circle is being traced out. Here the circle is being traced out at a uniform rate. Because basically because the derivative of a parameter with respect to t was 1. But now we're taking sine and cosine of an exponential function of t. How does the exponential function behave?
Flexible increase.
Growth or decay in this case? Because
So it's gonna slow down as opposed to.
no, it's going to go the other way. It's going to grow. Because the reason why the parameter values are always positive. When you plug in a positive number into exponentials, it's growth. Yeah, whereas negative arguments lead to decay. So it's going to start out relatively slow and then speed up. Here's another example of 3 sets of parametric equations that describe same curve, same function. Y equals x cubed. First one, x is equal to t. Y is equal to t cubed. Next one, x is equal to squared. Y is equal to t to the 6. And third one, x is equal to sine t. Y is equal to sine cube t. So in all 3 cases, you can see that the y value is the cube of the x value. But if I were to, and I'll let t range over all real numbers. Okay. So if I were to plot this, so here's this plain old y equals x cubed. Just forgetting about parametric equations, just plotting as a function of x. So if I were to plot these parametric curves, letting t range over all real numbers, I'm not necessarily going to get this because of how the functions involved behave. Now, for the first one, since x and t are the same thing, I effectively have y equals x cubed for x going from minus infinity to infinity. So the first set of parametric equations will give me the entire curve y equals x cubed. But what about the other two? Because whenever I plug in a t, I square it to get x. What does that mean about if I plotted this for all possible t? I'm not going to get exactly this, but what am I going to get?
All positive?
Yeah, the positive part, because x is going to be non-negative. So for whatever x I have, y will be its cubed. So I'll just get the right portion. Okay. What about the last one? Because since x is sine t.
So X is gonna, well. Oh. Gonna be between.
Yes.
-1 and 1.
Yeah, x is limited to that. And y is x cubed, so that's So we're only gonna get this portion of the curve, for x values, x and y values between -1 and 1. Okay. But here, but t still is allowed to go from -infinity to infinity. So if I let t go off to infinity, or I'm only getting this portion, what does that mean in terms of how this is traced out? Like if I start on a t equals 0, let's say, so I'm right here, then I get to t equals pi over 2. So x is 1, y is 1. So I have to trace out this portion. And then so it's a t will continue increasing. When t is pi, I'm back here. And then I let t continue increasing all the way to like for instance, to when t gets to 3 pi over 2, I'm down here. So as I let t continue increasing, what am I going to get in terms of points?
Keep tracing it as.
Yeah, it's going to trace over itself again, again, and again. So every cycle of t going from 0 to 2 pi will trace out the entire curve. Even then, it'll trace it out twice. Yeah, because really a period of pi is enough. Like if I let t go from like minus pi over 2 to pi over 2, that would give me this whole thing, but it's just gonna trace over itself. And so I don't get anything new after that. Is there any questions about how these parametric equations work so far? Right. During the rest of the time, we're going to look at how to go back and forth between describing curves as y as a function of x, or x as a function of y, and parametric equations. There'll be some homework problems on these too. Okay. So, define parametric equations. Or curve is called the asteroid, not asteroid, asteroid. So it's given by this equation, x to the 2/3 plus y to the 2/3 is equal to 1. And what that curve looks like is traces out that.
Hence the reason why it's called asteroid. It's not asteroid, but it still looks like a star. So
Yeah.
Asteroid.
We'll go with that. Okay, so way we can use get parametric equations from this is to relate this equation to the equation of a circle, because I can write this as x to the 1/3, the whole thing squared, plus y to the 1/3, the whole thing squared, is equal to 1. So when you have a sum of two squares equaling 1, then you can think of the two items being squared as cosine and sine of some angle. So what you can do is you can equate x to the 1/3 as cosine t, and y to the 1/3 equated to sine t. So that means I get, if I solve each of these equations for x and y, I have x is equal to cosine cubed t, and y is sine cube t. Because then if I raise x and y to the 2/3 power, I'll have cosine squared and sine squared. That's sum to 1. So if you have equation x and y that describes a curve, and it's possible to write it as a sum of squares, whatever's being squared equates to sine and cosine. So that's one way it works in admittedly limited circumstances. To get parametric equations from an equation in Cartesian coordinates. Then I could try that same approach. This next example. Find parametric equations for this ellipse. 4x squared plus 9y squared equal to 36. So how can we use a similar approach to what was done in the last example to come up with parametric equations for x and y?
2x, y.
Okay, so we have a sum of squares equaling 6 squared. Okay. Okay.
6 cosine.
Yes, so the x coordinates, what's being squared here, can be equated to radius times cosine t. Alternatively, I could have divided through by 6 squared and get some squares equaling 1. So 2x is equal to 6 cosine t. 3y is equal to 6 sine t, and that'll satisfy this equation. So now we have parametric equations for x and y. So if you plug in parameter values for t going from, for instance, 0 to 2 pi, if you scale cosine and sine by the same amount, you get a circle, but because you're scaling by different factors, you get an ellipse. Okay, so let's say you have it writing, I could have written this as 2x over 6, the whole thing squared, plus 3y over 6, the whole thing squared is equal to 1. And that'd be another way to arrive at the same conclusion. Okay, any questions about this one? Now we'll go the other way. We're given the parametric equations, and you want to describe the curve as y as a function of x or vice versa. Given these parametric equations, x is equal to t plus 2, y is equal to t minus 1. How it's described, like in a problem statement, is you eliminate the parameter t. And obtain what's referred to as a Cartesian equation. And for practical purposes, that refers to equation of form y equals f of x, or x is some function of y. Okay. Whichever one works. So what you do is, if you want y equals f of x, you solve your first parametric equation. So I'll just refer to these as okay. R1 of t, R2 of t, so whatever functions of t you're given. They solve your parametric equation of x for t. And then if y equal to R2 of t, and you substitute your expression for t, which t is now described as a function of x. Or t is R1 inverse of x. It's the inverse function of R1. So in other words, y is R2 of R1 inverse of x. That's how you can describe y as a function of x. And you can do the opposite if you want x as a function of y. In that case, x would be equal to R1 of R2 inverse of y. So you solve the parametric equation for y, as solve that for t, plug that t expression into your parametric equation for x. Now this is assuming that in whichever case you're using, that you, whoops, that should be R1 inverse. That function can be inverted at all. Maybe it can't be. So if R1 is not 1-to-1, in the case of y equals f of x, or if R2 is not 1-to-1, that's for the x equals a function of y case, then you're only going to get part of a curve. But for example, like the circle. Actually, I'll do an example right now. X is cosine of t. Y sine t. If I want to describe is y as a function of x. So I let t equal inverse cosine of x. But this is only 1-to-1 for x going from -1 to 1, and t going from 0 to pi. Because 0 to pi is the range of inverse cosine. So then I substitute my expression for t into the equation for y. So I have sine of inverse cosine of x. Now that's a bit of a mess to work with, but keep in mind that sine is plus or minus square root of 1 minus cosine squared. Okay, but now I have cosine of inverse cosine of x, and those will cancel out. So I get square root of 1 minus x squared. Okay. But I don't get the whole curve, because so if I choose a positive square root, I get the top half of the circle, but just negative square root, I get the bottom half. And this comes from cosine not being a one-to-one function. Questions about this example before I do other ones? Oh. I didn't finish this example right here. Oops. Okay, now, x and y are linear functions of t. So those functions are one-to-one. That helps. So, for y equals function of x, I'm going to solve first parametric equation, x equals 3t plus 2 for t. So what would t be?
X minus 2 over 3.
Yep. X minus 2 over 3. And then the y is t minus 1. So go ahead and substitute this expression for t. If I combine this into one fraction, I'll have x minus 5 all over 3. So now I have y as a function of x. So x and y are both linear functions of t, so we end up with y being a linear function of x. We got a line of slope of 1/3. Notice here we have dx dt equal to 3 and dy dt is equal to 1. And in general, dy dx is dy dt divided by dx dt. We'll talk more about that next time, but it's no accident that if you divide the slopes with respect to t, you get the rate of change of y with respect to x. So that's something that's in general for linear functions like these. So you could think of it as 1 over dt is canceling. Well, some mathematicians would not be very happy with me saying that. But it works. Okay, one more. And given these parametric equations, x is square root of t plus 1. Y is equal to e to the t. And we're going to assume that t is non-negative. So if I want to describe x, sorry, y is a function of x. So how do I begin?
Well, that's for you.
Yeah. X is a square root of t plus 1. for t. And what will I get for that?
Minus one.
Yeah, so t, it turned out to be x squared. That's what, so I square both sides to get x squared is equal to t plus 1. Just rearrange and you get t. Okay. So what does y turn out to be? As a function of x. Yeah, so e to the x squared minus 1. Okay. Now, square root function is not 1-to-1 in general, but because I'm restricting to t greater or equal to 0, on that domain, x function is 1-to-1. So I will get the same curve that these parametric equations described. Okay. So, but considering that t is greater or equal to 0, I'd like to have a domain for this function too. So based on this domain for t, what x values are considered here? And use the parametric equations to figure it out. It's more restrictive than that. Yep. Greater than or equal to 1. Yeah. Because once I plug in a non-negative value for t, I'm going to be taking square root of something that is greater or equal to 1. So the x itself will be greater or equal to 1. So that's the domain in that case. Now, if I want to go the other way, x is a function of y. So now I'm going to solve the y equation for t. So what is t? Yeah, natural log of y. Okay. All right. So then I just go ahead and plug that into my equation for x. Natural log of y plus 1. Okay. But I need a domain for y. So if t is greater or equal to 0, what's my domain in y? Yeah, y is greater or equal to 1 because if I substitute a non-negative number to be exponential, I'll get a y value greater or equal to 1. Okay. And that's all I got for today. Even though the time was short, that felt like enough anyway. Maybe some Mondays.
In class.
Okay, all right, well, good, thank you. That's right. So we're doing calculus and parametric curves on Wednesday.
All right, and we better be done with our homework by then.
I guess so, yeah.